Welcome to this Skill Builder session on normal distribution. In this session, we'll be covering what a normal distribution is and the properties or key characteristics of normal distribution. I'll also explain how a normal distribution can be standardized by converting its values into z-scores. Normal distribution is an important assumption of parametric tests. By checking that the data in our sample are normally distributed, we can be more confident that the results of our analyses, so specifically the p-value, is valid. A distribution allows us to find the probability of obtaining a certain value or making a certain observation. Population parameters are what make up a distribution. You could imagine that this curve represents people's heights, so we could use it to determine the probability of observing someone who's really short, really tall, or somewhere in between. And when data are normally distributed, the mean, median and mode are exactly the same. Half the values fall above and below the mean, so it forms a bell curve like this. And the mean and the standard deviation are the two parameters that determine the shape and the probabilities of the distribution. And there are lots of different things that are normally distributed, including height, commuting time, time to complete a race, and so on. The larger the standard deviation, the wider the curve. And when there's a wide spread of data, each observation or measurement could be quite different from one another, like in our example of people's heights. A small standard deviation determines a narrow curve, and when there's a narrow spread of data, the value of each observation won't be so different. So an example of a narrow normal distribution might be if I were to go and pick out multiple Coke cans from a vending machine and then measured exactly how much liquid is in each one, each of my measurements or each of my observations won't be hugely different from one another. So the distribution of these values, or the spread of the data that I plot, would be very narrow. And the Skill Builder on descriptive statistics covers variance and standard deviation if you'd like to learn more about those. There's an empirical rule in statistics, which is that in a normal distribution, 68% of your observations lie within one standard deviation from the mean. 95% of your observations lie within two standard deviations from the mean, and 99.7% of your observations lie within three standard deviations from the mean. A normal distribution can be converted into what's called a z-distribution, and this is what allows us to determine the probability of observations occurring, and it lets us compare different data sets as well. I won't go into the detail of how this is calculated, but the way that it works is it transforms each data point into a z-score, and a z-score quantifies how many standard deviations a data point is from the mean. For example, we could convert an observation into a z-score of minus 1.35, which is less than 1.35 standard deviations from the mean. Then we can look up that z-score in a probability chart, which tells us the probability of observing a value lower than a given observation. And the way that this works is we'd first look up the minus 1.3 part, then we'd look up the 0.05 part to find the associated probability. In this example, that's 8.85%. So that means that there's an 8.85% chance of observing a value to the left of the z-score in this distribution. Sometimes data are not normally distributed, and instead the distribution might be skewed. This is when data points are spread far from the mean in one direction, which could be either above or below the mean. If the distribution is negatively skewed, there's a longer tail on the left, because one or more measurements are extremely low. Or if the distribution is positively skewed, then there's a longer tail on the right, because one or more of the measurements are extremely high. There are a couple of different reasons why a distribution might be skewed. The first is that some population data are just not normally distributed, and instead might follow what's known as the Pareto distribution, where a small percentage of observations impact the overall distribution. Data that follow a Pareto distribution have a lower bound, which means that there's a minimum possible value, and there is no upper bound with a long tail that extends into positive infinity. One example of Pareto distributed data is income, where a small percentage of the population have a very high income. So those scores that are much higher than the mean positively skew the data. Sampling bias could also result in a skewed distribution. For example, if you're interested in average income in the UK and you only collect your sample from a certain area, then your sample might not accurately represent the UK population. Another reason for a skewed distribution could be because there are outliers. An outlier is an extremely high or extremely low value compared to the rest of the data. This pulls the distribution towards that extreme value and disproportionately influences the mean and the median, and outliers can make the spread or the variability of the data appear larger than it actually is. Sampling bias could also result in a skewed distribution. For example, if you're interested in average income in the UK and you only collect your sample from a certain area, then your sample might not accurately represent the UK population. Another reason for a skewed distribution could be because there are outliers. An outlier is an extremely high or extremely low value compared to the rest of the data. This pulls the distribution towards that extreme value and disproportionately influences the mean and the median, and outliers can make the spread or the variability of the data appear larger than it actually is. For guidance on the broader range of stats tests, please go to the Skills for Academic Success website at kent.ac.uk/SAS, where you can view more of our numeracy and statistics videos. You can also book a one-to-one appointment with one of the SAS team.